This is the first video for Unit 2. We're going to look here at some inductive reasoning. So your learning target, please go ahead and write this down. Your learning target for this lesson is going to be using inductive reasoning to make conclusions. This is lesson 2.1. And Unit 2 is going to be about logic and probability. Logic and probability sometimes don't really seem like math because we're used to adding, subtracting, multiplying, maybe even solving for x like we did in Unit 1 quite a bit. But this unit is just going to have us thinking and kind of using some of our reasoning skills in order to prove things are true or prove things are not true. Okay, so even though it doesn't seem like it's math, it's a sort of math where we're doing a lot of problem solving. So problem solving skills look a little different, and they're going to definitely look different in this unit. Make sure you're using a pencil, please, and that's true for all of your work in geometry. And then we have 3 vocabulary terms. The first one is going to be conjecture. A conjecture is an unproven statement that is based on observations. So anytime we're doing inductive reasoning, we're using observations or we're looking at patterns. Okay? Next vocabulary is you use inductive reasoning when you find a pattern in specific cases, and then write a conjecture for the general case. So you can see that conjecture and inductive reasoning kind of go together. So the word observations and the word patterns are going to be things that you want to remember for inductive reasoning. We're going to learn about a different type of reasoning in a couple lessons, so think about observing things and noticing patterns. That's the kind of thing you're doing when you're doing inductive reasoning. The third vocabulary term is going to be counterexample. A counterexample is a specific case for which a conjecture is false. So it's kind of an example that proves that your thinking is incorrect or a statement is incorrect, because there's an example that can prove that it's incorrect. All right, let's take a look at this first example. It says to describe a visual pattern. So if you're looking at the pattern here, notice that the dot is in the upper left, then it's in the upper right of the 4 squares, then it's in the lower right of the 4 squares, and our directions say sketch the next figure in the pattern. Well, I can draw a circle, and I can draw my 2 lines that are intersecting there at a 90-degree angle, it looks like, and then my dot needs to be drawn in the next square, or next portion, next quarter. So this was the first quarter, it moved around to the second quarter, in the second picture it moved to the third. So now I'm going to go ahead and draw my dot in this quarter, and that would be showing that I can recognize a visual pattern. And there's one for you to try on your own with the dice. Well, it looks like dice, it's not exactly dice though. I'm going to go down here to example number 2, describe a number pattern. So if I'm looking at the pattern 2, 8, 32, 128, and we need to write the next 3 numbers in the pattern. Okay, so 2, how did we get from 2 to 8? Well, we could say that we added 6, or we could say that we multiplied by 4. So let's look at the next number. We did not add 6 to get to 32, right? 8 plus 6 is not 32, but we could say that we multiplied by 4. So it looks like the pattern is multiply by 4 to get to 8, multiply by 4 to get to 32, and if we multiply by 4 again, we are going to get to 128. So I just have to take and multiply by 4 this number, and 128 times 4 is 512, so that's my first of the 3 numbers that I have to add into this sequence. And then the next one, if I multiply 512 by 4, I get to 2048, and if I multiply that number by 4, then I arrive at 8,192. So first of all, in each one of these you want to recognize the pattern. Okay, how did you get from one number to the next? And then it asks you to write three numbers in the pattern, the next three numbers in the pattern. So you're looking for that in numbers 2 and 3 here, and I'd like you to try to practice these on your own. If you have questions, if you can't quite recognize the pattern, please make sure you ask in class, but you need to ask specific questions so that I know that you at least made an attempt to do these problems on your own. So besides just being able to look at a pattern and actually come up with the next shape in the pattern or the next few numbers, we should also be able to come up with a conjecture or an educated guess about a specific topic. So on the back here of your note sheet, example number 3 says make and test a conjecture. And we're going to do that about the product of any two odd integers. Well, the first thing we need to make sure we know is odd. Odd is 1, 3, 5, anything that's not divisible by 2. And an integer is a non-fractional number or non-decimal number. It's a whole number basically. Okay, so it's non-fractional. So it could be, like I said, 1, 3, 5, etc. Now product means that we're going to multiply. Okay, so we're going to take two odd integers and we're going to multiply them together and see what happens. What kind of numbers do we get when we multiply two odd numbers together? Well, we're going to find a pattern using a few groups of small numbers. So 3 times 13 is 39, 7 times 21 is 147, 5 times 9. Remember, I have to use odd and integer numbers. And then 11 times 15 is 165. And my conjecture, this is just in the example here, the conjecture is the product of any two odd integers is odd. Okay, so anytime we multiply two odd numbers together, we end up getting odd. And then it says test your conjecture to make sure that it works. Okay, so we said 17 times 9 is 323, that's also odd. 23 times 31 equals 713, that's also odd. So we've basically proven, by just using a couple of examples here, that the conjecture is true, and when we multiply two odd numbers together, we get an odd number result. Okay, I'd like you to try these on your own, but I would like to do one of them with you. So it says here, number 4, make and test a conjecture about the product of any two even integers. Okay. So thinking back to the one that we just worked on, which was the product of any two odd integers is odd, could you make a conjecture? A conjecture, remember, is just an educated guess. Could you make a conjecture that the product of any two even integers is even? Okay, so I'm just making an educated guess because I've noticed it, but I'm going to actually put together a little test. My little test is 4 times 6, those are both even, they're both integers, equals 24. Okay, 24 is also even. Let's see, we could also do 12 times 20, which is 240. Even, the result is even. And some bigger numbers, 30 times 40, those are both even, both divisible by 2, and that equals 1200, or 1200, also an even number. So I had to come up with a conjecture, and then I had to test and make sure that those can prove that my conjecture is correct. Okay, and I'd like to have you try number 5, write a conjecture, and also give a few examples when you're testing your conjecture. Okay, the last part of our notes here is finding a counterexample. A lot of students have a difficult time with this because you're finding a time where the statement is false. So this is mostly true. Okay, all odd numbers are prime, but there are some situations where odd numbers are not prime, and that's what you're trying to find, proving that the statement is not always true. So a counterexample proves a statement is not always true. It can be a conjecture, but it's not necessarily something that is correct 100% of the time. Okay, so when we look at all odd numbers are prime. Well, let's write a few of the odd numbers. 1 is an odd number. 3, 5, 7, 9, 11, 13, 15, etc. So these are odd numbers, but are they all prime? Prime means that they don't have any factors except 1 and themselves. So I can see right now that 9 is odd, but it is not prime. Remember, 3 times 3 is 9. Okay, that makes it not prime. I also see 15 here, and 3 times 5 happens to be 15, so that makes that one not prime either. So actually I came up with two counterexamples, the number 9 and the number 15. Those both are proof that the statement all odd numbers are prime is not always true. So I'd like you to find a counterexample to show that the difference means subtract, the subtraction of two positive numbers is always positive. Okay, so that means that you need to find how the subtraction of two positive numbers is not always positive. So you have to find something that would result in a negative value. All right, and I'll leave that up to you. Now, if you have any questions about counterexamples, inductive reasoning, finding patterns, anything like that, please make sure you ask.